Okay, two other quick corollaries of the mean value theorem. This one says you got yourself a differentiable function. If it's differentiable, it has to also be continuous. Remember, differentiable implies continuous. You can have continuous but not differentiable, but you can't have differentiable and not continuous. Think really hard about that. Make sure you understand the difference. So you've got a function that's differentiable on some interval. I don't care if it's closed or open. This corollary says if your derivative is always zero on the entire interval, then you've got yourself a constant function. So this one should be kind of obvious. Remember, the derivative equals zero means you've got a horizontal tangent line. If the derivative is always zero, then your function's not changing. So your function was horizontal at least once, and then it never changes. It's going to stay horizontal. Okay, and here's the proof. We do it by contradiction. So you can read through the details if you want. But the proof is, suppose it's not constant. Suppose that the average rate of change is not zero. So your starting and ending points are different. Then by the mean value theorem, there's going to be some spot in the interval where the derivative at that spot is equal to the average rate of change. But we just said that this is always going to be zero. That was the necessary condition for the theorem. So there's no way this thing could be not zero if this is zero. Therefore, we have a contradiction. So this is an if and only if statement. This works both ways. Constant functions have zero derivative. And if your derivative is zero everywhere on some interval, then you've got yourself a constant function. So you've got some function. I don't care what it's doing through here. Like it's doing all kinds of crazy stuff. But from say here to here, A to B, on some interval I, that function doesn't change. It's a horizontal line if and only if the derivative is zero everywhere in that interval. Hey, then another corollary that is derived right from that one. Suppose you've got yourself two functions, f and g, and you somehow know that the derivatives are the same everywhere on some interval. So two functions have exactly the same derivative on some interval. Then the conclusion is you've got yourself the same function up to an additive constant. And the proof is based on that last corollary. I define this auxiliary function, h equals f minus g. Take the derivative, h prime would be f prime minus g prime. Well, since those are the same, that's our condition for the theorem, then the difference of those derivatives must be zero. Well, if the difference between them is zero, so h prime is zero everywhere, that satisfies this condition. That means h must be constant. So this auxiliary function, h here, must be constant. F minus g must be a constant. Therefore, f equals g plus some constant. So what this is saying is you've got yourself two functions. So maybe here, I'll draw the functions and then I'll draw their derivatives or some derivatives. So you've got yourself two functions and the slope of the tangent line at every point on f is the same as the slope of the tangent line on g at every point. So I just pick a random spot. His tangent line might look like that. Maybe he has a slope of 1.5. If I go up on g at that spot, exactly the same slope. The only way this is possible is if this is really just the same graph shifted up and down. G must be f plus or minus some constant. C here could be negative. Okay. Or another way to think of this, maybe we're looking at the pictures. Here's the picture of f prime, not necessarily that f prime. I'm just drawing some function. It's derivative. We got some derivative. It looks like this. And then we come along and we just happen to know that we've got some other function g and his derivative looks like this. If two functions have the same derivative, they don't necessarily have to be the same function. They might differ by a constant. So same thing, g will be f plus some constant. And again, that constant might be 0. They might literally be the same. Or it might be a negative number, it might be a positive, any of those. This is going to be really important when we get to antiderivatives. This is where we're really going to see this play out. When we take an antiderivative, we don't get one single function, we get an entire family of functions, and we're always going to get a plus c, and this is the reason why. And this all comes from the mean value theorem.